Thank you very much, Bruno, for organizing this beautiful event. I think the title of my talk is I was hoping you would remember it. I think it's something like weight structures and formality.
Weight structures and formality.
Exactly, okay. So I will discuss various certain ideas that you can use to prove formality results using inputs from algebraic geometry. And I think the first result in that direction is the very famous paper by Dolin, Griffiths, Morgan, Sullivan, where they prove formality of compact Kähler manifolds using Hodge theory. And so that's the first thing I'm going to talk about today. But even before that, let me just remind you what the definition of formality is. Well, you can make the definition over any, say, commutative ring. And let me fix P an operad in R modules. Well, here's the definition. A DG P algebra A is formal if there exists a zigzag of P algebra quasi-isomorphisms connecting A to the homology of A. So a zigzag, well, there will be a map that can go either way, but requires that all of them are quasi-isomorphism. And we require that all of them are maps of P algebras. So that's why, for this definition to make sense, I need P to be actually concentrated in degree 0 because I need to have a P algebra structure on the homology. So the homology is a lax monoidal functor. So if A is a P algebra, the homology will be a P algebra in the category of graded R modules. And in particular, I can view it as a P algebra in the category of chain complexes, where I give this guy a 0 differential. Okay. And in fact, so well, in this definition, I have an arbitrary zigzag, but you can prove using, for instance, model category technology that any such zigzag can be reduced to a length 2 zigzag. So it's a remark. So if there exists such a zigzag, there will in fact exist a zigzag which is only of length 2. To a length 2 zigzag. And the argument for this is, well, whenever you're in a situation where you have a model category structure on DGP algebras, well, what you can do is, so such a zigzag is actually giving you an isomorphism in the homotopy category, and we know that in a model category, any isomorphism in the homotopy category can be represented by an actual weak equivalence between a cofibrant replacement of the source and a fibrant replacement of the target. And in those model structure of P algebras, any object will be fibrant. So in fact, you just have to take a cofibrant replacement of the source, and then you will be able to produce a weak equivalence, a quasi-isomorphism of P algebras from that cofibrant replacement to the homology. And let me make a slightly different definition. So this definition, well, I don't know where it first appeared. I learned about this definition in a paper by actually 4 authors from Barcelona. Gillian, Navarro, Pascal, Deutsch. So, well, I'll cite this paper a lot in this talk, so I will abbreviate this to GNPR from now on. And the definition is of a formal functor. So let's say, let's take C to be a symmetric monoidal category. A formal functor, so sorry, a lax modular functor f from C to chain complexes over R is formal if there exists a zigzag of lax monoidal natural transformations that are also object-wise quasi-isomorphisms. Connecting, can you read when you're right here? Yes. Connecting F to homology composed with F. Yes? Oh, sorry about that.
Okay.
Oh, because of the screen, sorry. Okay. So here's a definition. So F is a lax monoidal functor from C to chain complexes over R. As I said before, the homology functor is a lax monoidal functor from chain complexes, say, to graded R modules. So if I compose 2 lax monoidal functors, I still get a lax monoidal functor. And then I require that I have a zigzag connecting F. So a zigzag of natural transformations of lax monoidal functors connecting F to H composed with F. And of course, in this definition, C, it will make sense. The examples we'll see, maybe C will be a usual category, so a set enriched category, but it would also make sense if C is an R modules enriched category. So an R module enriched symmetric monoidal category, and then the functor here would be enriched over R modules. And in fact, these two definitions are, this definition is in fact, this definition is in fact more general than this one. If you allow your operands to be colored, so let's say definition 2 is contained in definition 1. for the following reason. So to any, so maybe it's a construction that is maybe not familiar to everybody, but it's very easy actually. For any symmetric monoidal category, I can view it as an operad, and then an algebra with a operad is exactly the data of a lax monoidal functor over your symmetric monoidal category. To any symmetric monoidal category C, I can associate an operad with a set of objects with a set of colors. The objects of C and my multimorphisms. So a multimorphism from C1, Cn to D will just be an actual morphism in C from the tensor product to D. And the claim is an algebra over this colored operad is exactly the same data as a lax monoidal functor over C. So in fact, if in this definition here I allow colored operads, it's actually more general than this definition.
I'm sorry, second definition, not necessarily functors, which are sure functors associated to an operad. So you use the one is including the other and a bit lost. Which is one, which is two?
This is one, this is two.
Yeah, exactly. This seems to be a bit more general, no? And not
Yeah,
every functor are like.
No, I'm saying any. Yeah, I'm saying a lax monoidal functor is the same data as an algebra over the underlying operad over on this category. Yes, so of course, as usual, feel free to interrupt me as much as you want with questions and remarks. Okay, so yes. So yeah, a lax monoidal functor, you have the data of a morphism. Yeah, exactly. So if they were iso, that would be a strong monoidal functor. In this definition, I just require that they're lax monoidal functors. Yeah, so for instance, the homology functor is lax, unless you're over a field, the homology functor is lax monoidal, but not strong monoidal. All right, and but this second definition is, I mean, in some way, so the implication goes both ways, because this second definition lets you deduce formality results for P algebras. So far what I'm saying is very formal. So it's a remark that you can make is if you have a functor that is formal, so is a formal lax monoidal functor. And if you have, if A is a P algebra in C, then f of a is a formal P algebra in chain complexes over R. And the proof, well, there is almost no point of writing a proof. So the proof, you just, by assumption, you have such a, you have a zigzag of quasi-isomorphism connecting F to H composed with F. And if you evaluate this zigzag on A, that will give you a zigzag of quasi-isomorphisms of P algebras connecting F of A to H of F of A. So a Lax-monoidal functor sends P algebras to P algebras. That's exactly what Lax-monoidal functors do. So you just evaluate the zigzag connecting F to H composed with F on A. And that gives you a zigzag connecting F of A to H of F of A. All right. So now I can state two theorems that are very much related. There's somehow one is covariant and one is contravariant. So there are two theorems. They can be stated as formality of some functors. So theorem one is historically the first theorem, the first of these two theorems. So it's Deligne, Griffith, Morgan, Sullivan. And the theorem says the following. So let K A umlaut H be the category of compact Kähler manifolds. So compact Kähler manifolds are complex manifolds that are also Riemannian manifolds and symplectic manifolds in a compatible way. If you're not familiar with this, you can just, one useful fact is that compact Kähler manifolds contain smooth projective algebraic varieties. Okay, so what is a theorem? The theorem says that the RAM functor, and I'm going to denote it by curly E, from compact Kähler manifolds. So this is just real the RAM complex, so take differential forms, real differential forms. So this is a contravariant functor, and it goes to chain complexes over the reals. It turns out that this functor is Lax monoidal, and this functor is formal. Okay, and now let me state the covariant version of this theorem. So this is the GNPR version. So what they prove is the functor of singular chains with real coefficients so this is a functor that goes from you restrict it to compact. Of course, it's defined in any topological space, but you can restrict it to compact Kähler manifolds. And this is a Lax monoidal functor to chain complexes over R, sorry. And this functor is formal. So I will give you a sketch of a proof of these two theorems today. But first, maybe I want to discuss some consequences. So of course, well, the Deligne-Griffiths-Morgan-Sullivan theorem tells you that it tells you that the real homotopy type of objects of compact Kähler manifolds is determined by their real cohomology with respect to the cup product. By their cohomology viewed as commutative algebras in graded vector spaces.
We have a question on the chat. Clemens has been asking, is this not a strong monoidal? Which one to Clemens? I'm sorry, I got lost. Clemens, which one would you like to be strong monoidal?
The covariant functor.
The singular chain is not strong monoidal. I mean, it's strong monoidal up to in a homotopical sense. So the comparison map from chains on X tensor chains on Y to chains on X cross Y is a weak equivalence. Okay. But it's not a strong monoidal functor. Like in the one categorical sense, it's not a strong monoidal functor.
Thanks.
But yeah, I will say more about this at the end of the talk. Right. So yeah, we're discussing this this consequence here, and well, the way you prove this. So for instance, what this is saying, you can actually compute the homotopy groups of a compact Kähler manifolds tensored with R. If I give you the data of their cohomology as commutative graded algebras. And the way it works is just, well, the homotopy groups. So let's say X is pointed and simply connected, so that I don't have to worry about pi 1. So the homotopy groups of X tensored with R, there will just be the homotopy group. So homotopy groups of well, the Sullivan realization functor applied to the cohomology of X with coefficients in R. So yeah, you have this Sullivan functor that goes from say simply short sets to CDGAs over Q, well, you can extend it to, well, you can do a real version as well, and there is an adjoint to this functor, so it turns a CDGA to a simplicial set. So depending on where you put the op, it's a right or left adjoint. Yeah, what I'm saying is you can just recover the homotopy groups of your compact Keller manifolds. There will be the homotopy groups of the Sullivan realization of the cohomology. But and of course, I mean, all the data, I mean, this will be compatible with all the additional structure that the homotopy groups have, like for instance, the Whitehead Lie bracket. So on this side, you have a Whitehead Lie bracket. On this side, you have one as well. And this isomorphism will be compatible with this data. But it's, what we're seeing is even better because it's not just a statement for each compact Keller manifold individually. Since it's actually my functor which is formal. In fact, for instance, if I have a map between two compact, like a smooth maps of complex manifolds between two compact Keller manifolds, the homotopy type of that map will also be captured just by the data of the cohomology functor applied to that map. So for instance, if, like, let's look at a simple example. If you say you have a compact Keller manifold with an action of some discrete group, this isomorphism will be equivariant, for instance, with respect to the action of that group. So this functoriality statement is really, it contains much more data than just saying each compact Keller manifold is formal individually. Right, and maybe let me state one consequence of the covariant version. The morphisms are smooth maps of complex manifolds. So they have to be compatible with a complex structure. Yeah, it's not just going to be any smooth map. They have to be holomorphic. Right, so let me give a consequence of the covariant version. So maybe it's the most striking consequence is the following. So the way they apply this general result is, well, using the remark I've made earlier, well, it's actually still on the board. Any operad, so if, sorry. If O is an operad in compact Keller manifolds, so this category of compact Keller manifold it's a symmetric monodal category and their Cartesian product. So what I mean by an operad there is just, well, you can make sense of the definition of an operad in any symmetric monodal category. So I require that the operad composition maps are maps of Keller manifold, therefore they're smooth, they're holomorphic maps. If O is an operad in compact Keller manifold, then Shen's an O with real coefficients is formal as a DG operad. And in fact, well, it's something I'm going to talk about a little bit later in the talk, but you can even deduce, in good cases, you can actually deduce formality of singular chains with Q coefficients. once you have formality of singular chains with R coefficients. And this kind of result, well, one very nice example that fits in this principle is you can take O to be the operad of compactified moduli spaces of curves. So let me just say, well, so M0n is the moduli space of genus 0 curves with n marked points. So up to isomorphism, there is just one genus 0 curve, which is the projective line. So this is also the same as the space of, so yeah, any object in this category will be, you give yourself n points, n distinct points on the projective line, and then you mod out by automorphisms of the projective line. So this is the space of configurations of n points on P1. So this is a complex projective line. Modulo, well, PGL2. Well, yeah, you mod out by the automorphisms. One. It turns out that you can be very explicit about this. The group of automorphisms of P1. So whenever you have a configurations of points on P1, you can find an automorphism that puts the first one at 0, the second one at 1, the third one at infinity. So this space is actually isomorphic. And this, yeah, once you fix the image of 3 distinct points, an automorphism is completely determined. So in fact, this space is isomorphic to the space of configurations of n minus 3 points in P1 minus 0, 1, infinity. And that's it. So no automorphisms now. So maybe I should say, yeah. Usually these moduli spaces, they're not defined for n smaller than 3. So, well, this space actually, so you see from this description, you see it's actually a complex, very nice, it's even an algebraic variety over the complex numbers, even over the rationals or the integers. It's not compact though. So it doesn't fit in the picture, but that's why I have this bar here. So yeah, these varieties admit nice compactifications. So M0n is a subvariety of M0n bar. And M0n bar is the moduli space of genus 0 curves with nodal singularities with n marked points. So I'm not going to go too much into details about what this means. Maybe, yeah, just one important fact that I require that my points, they don't live at the singularity, they live in the smooth part of the curve. But what does a J0 curve with no singularity look like? So you can draw a picture. So a point in M0 and bar looks like, so it will be a bunch of P1 glued together along some points. So each of this blob is a P1. It's actually a two-sphere. Yes.
And then I was asking the question, does this theorem mean the chain little and this quadratic is quantum?
I'll talk about this in a minute. So no, well, yeah, yes and no. Yeah, so the problem is that the little disk operator is not, at least in an obvious way, an operator. Well, of course, it's not an operator in compact Keller manifolds. But it turns out you can build some models that are almost as good. Right, so the point looks like some kind of tree where, so made of two spheres glued together, and then you have some mark points, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, something like this. Okay. So in particular, if you just have one blob, one sphere, then you get a point. So the subspace M0n without bar is really just a subspace where you just have one blob in your curve. And the great thing about these modular spaces is that they form an operad, because whenever you have two such curves, you can glue them. If you pick a point, one of the mark points in each of them, you can actually glue them along these two mark points, and you get a new curve with more blobs. So it's even better than an operad. It's actually a cyclic operad. So these modular spaces form a cyclic operad. Right, so now we can apply this theorem over here, and we know that the DG operad of chains on these modular spaces is formal. So it's quasi-isomorphic to its homology, and its homology, we know it. It's what's called the hypercommutative operad. And maybe, well, let me give a word of motivation for why you might care about a DG operad being formal. So, if a DG operad P is formal, so maybe for this to hold, let me assume that my so over a base field K of characteristic 0. If a DG operad P is formal, then there is a so let me phrase it in terms of the language of model categories. There is a Quillen equivalence between algebras over P and algebras over the homology of P. Or maybe more accurately, there will be a zigzag of Quillen equivalences induced by my zigzag. So in particular, well, an algebra over P might be something that looks very complicated, but if you know that your operad is formal, you know that you'll be able to represent any such algebra by something which will be over a much smaller operad, like an operad you can actually describe without any homotopy theory, so just an algebraic gadget. So for instance, this result tells you that algebras over chains on these moduli spaces, they will be equivalent to just hypercommutative DG algebras. Okay. All right. So now I would like just to give you an idea of how these two theorems are proved. Maybe I'll just explain the DGMS, the Lin-Griffith-Morgan-Sullivan theorem. The other one is sort of similar. You just somehow dualize the proof. Yes, let me erase this. What?
The case where K is not a zero, you need to have the spheroid and the homology of the spheroid is the class from all of the
Yeah, well, there are two problems here. There is, because for you mentioned, if your ring is not even in a field, then yeah, you need some flatness hypothesis. But there are also problems with symmetry group action. So yeah, there are some results. Yeah, you will need to assume something like the symmetry group action being free. So maybe yeah, you will need flatness not over just the base ring, but the group ring of the symmetry group, something like this. So yeah, the proof of the Deligne-Griffiths-Morgan-Sullivan theorem, it relies on Hodge theory. And it can be nicely, all the Hodge theory you need, it can be nicely encoded in just one lemma called the DDC lemma. Right. So since your manifold is actually complex, it means that the tangent space of the manifold is not just a real vector bundle, it's actually a complex vector bundle. And you can encode this data as being a complex vector bundle as having an endomorphism of your vector bundle that squares to negative identity, minus identity. So you have a morphism J. So if M is a complex manifold, you have an endomorphism J from Tm to Tm, which squares to negative identity. So it's a real vector model endomorphism. And this J, well, you can dualize it, and it induces an endomorphism of the cotangent vector bundle. And then the RAM complex is just built out of the like it's just how do you call it? Well, it's just, you take the free algebra on Tm that you put in degree 1, Tm dual that you put in degree 1. So if J will induce an automorphism of the RAM complex. And then you can define, so the RAM complex has its usual differential, but it has, there is another operator which is called DC, which is by definition J inverse. You just conjugate D by J. And now, well, there is a lemma called the DDC lemma. So let me look at my notes that I stated properly. If X is a form, a differential form, such that dx equals 0, and x equals dcy. So x is closed under D and exact under DC. Then x equals d dc of z for some form z. So that's a lemma, and I'm not going to explain any, like, it's just the whole machinery of Hodge theory gives you this. And this uses some analysis of elliptic operators, so it's very orthogonal to what I'm talking about. But yeah, let's take this as a black box. Yeah, and there is, I mean, yeah, this D and DC play sort of a very symmetric role. So you actually have a dual or symmetric version where if x is a form such that dcx is 0 and x is dy, then x will be also of the form ddc. Yeah, also, yeah, one remark I should make is that ddc equals minus dc d. So x is of the form ddcz or dcdz. So you have a symmetric form of this result. So now I can prove DGMS. So now I can consider, so I have E star of M, the RAM complex. It contains something which I'm going to denote E star upper C of M, which is the kernel of DC. So in each degree, I just take the kernel of DC. It turns out that this is a subcomplex. And then this will subject to something which I'm going to denote, I think, by cohomology C of M. So each of these complex is equipped with a D differential. And this, so this is modulo the image of DC. So my claim is that these two maps, so this inclusion and this projections, they're quasi-isomorphisms, and this complex has a zero differential. So 1 and 2 are quasi-isomorphisms, and D is 0 on star C. Yeah, so this property of almost commutation of D and DC, it tells you that D induces a differential on this kernel, and it also induces a differential on this quotient. But it turns out that it's when you reach this quotient here, D becomes 0. And let me see how much time I have. Do I want to say a few words about this? When am I supposed to stop, Bruno? I started at 11, right? Or, okay. Yeah, so maybe I'll just, so it's a fun exercise to prove these claims using the DDC lemma. So I'll leave it as an exercise. And that concludes the proof. So now I can just say a few words about the covariant version of the theorem. So covariant version sort of uses the same ingredient. You need a covariant version of the DRAM complex. So sorry, not DGMS, GMPR. So, well, what you do is replace E star of M by its topological dual. So you get a complex that they call Durham current. So using their notation, it's called D lower star of M prime Durham current. And using the same proof as before, as for DGMS, that this D lower star prime is a formal functor. And then, so this is not quite the statement I had in the theorem I've stated. I was stating a theorem for a singular chain functors, a singular chain functor, and so then you can also compare D lower star prime to singular chains with coefficients in R. So you can show that they're also quasi-isomorphic as lax monoidal functors, and this uses standard techniques of integration of differential forms. So whenever you have a simplex on your manifold, you can integrate a differential form over it, and this gives you a comparison between these two functors. Yeah, so that's how you prove GNPR. Yes. Yes. Yeah. Yeah, so they don't state it in the paper. I don't know if this D prime is really on the nose of core algebra. I haven't really thought about this. But if it is, then I mean, yeah, the point is that of course singular chains will not be a core algebra on the nose. But it could be true that the upper prime lower star is a coalgebra, commutative coalgebra. Yeah. I believe it's going to be a coalgebra. Yeah. Yeah, definitely morally true. Yeah. Right. Okay. Are there other questions so far? So now I'm going to talk about these weights that are in my title. So yeah, this paper GNPR, so it does what I've said, but it also does something really interesting, which is they have a result of descent of formality. So I've already studied the result in the particular case of this operator of moduli spaces. They don't just prove that it's formal, that singular chains over it with real coefficients is formal. They actually deduce from this that singular chains with rational coefficients is also formal. And this result of descent of formality, it uses some important ideas. And one, yeah, you see this theory of weights appearing. So I'm going to give you essentially an equivalent definition of formality in terms of weight decomposition. So maybe from now on I work, my base ring is always going to be a field because I don't want to think too much about general rings. So, and let me denote by graded vector spaces the category of graded vector spaces. GR_vect is the category of graded vector spaces. But the grading, I'm gonna call the weight to, because I will also be homological grading, the homological grading of my objects. So this category of graded vector spaces, it's an abelian category, a k-linear category. It has a tensor product, which is the usual formula that you know. Right. Sorry. So now let me make a definition. We say that a chain complex. So this will be my notation. So I'm going to denote as an index the homological grading. And as an exponent, the weight grading. We say that chain complex in graded vector spaces is pure if the nth homology group of C. So since the category of graded vector spaces is an abelian category, the homology group of a chain complex in graded vector spaces will be themselves graded. So if this homology group is concentrated in weight n for all n. And then we have a theorem so the forgetful functor from chain complexes in graded vector spaces pure. So this is a full subcategory of chain complexes in graded vector spaces that is spanned by pure objects. Of course, whenever I have a chain complex in graded vector spaces, I can forget the weight grading and just do it as a chain complex over K. This functor is formal. And maybe in the interest of
sorry, can I ask a question?
Yes.
So sorry, Geoffroy, this is Alexandra. Could you say what, I mean, so in my lectures, I also use weight gradings, but we should perhaps be careful to distinguish these. So the differential in your setting has weight 0, is that correct?
0, yes.
Yeah, so in my lectures, the differential had weight -1. So this is not the same kind of weight that I've been considering.
I agree.
I just wanted to point that out. We're using the same terminology.
Yeah, I don't know a better name for it, so I'm just going to stick with weights. Yeah, so this theorem, well, maybe it's not a theorem, yeah, it's a proposition, but I leave it in the exercise. So it's really not very difficult. But from this result, you can deduce the following. So maybe I should have made the remark that, of course, so you have a tensor product, like a symmetric modular structure on chain complexes and graded vector spaces, just induced by the tensor product of graded vector spaces. And of course, pure objects are going to be stable under tensor product because the QNF isomorphism is going to be additive with respect to weights. So if you have something which is pure, if you tensor two pure things, you still get something pure. So this theorem is really is formal as a lax, like the definition I had at the beginning, a lax monoidal functor. So now, in general, I can say that a functor f from C to chain complexes over K. As before, this is a symmetric monoidal category. Is formal if it is, so I'm going to say weakly equivalent, meaning it's connected by a zigzag of natural transformation that are morphisms of lax monoidal functors. So weakly equivalent to F tilde that admits, in fact, it's an if and only if, that admits a factorization C. So my F tilde goes from C to chain complexes. And my factorization goes through weight graded and complexes. And this is the forgetful functor, and this is some other functor. So if I can factor my functor F tilde like this, it will be formal, and it's actually an if and only if, up to a weak equivalence. And the proof really follows from this result here. Whenever you have such a factorization, so you have a zigzag connecting the forgetful functor and homology composed with a forgetful functor. So if you precompose this zigzag with G, you'll have a zigzag connecting homology of F tilde to F tilde. And well, this proposition would be completely useless if we didn't have methods for producing such weight decompositions. And it turns out that there are sort of two ways that you can use to produce such decompositions. One of them using, yes, I think there is a question. Oh yeah, of course, yes, thank you. Very good question. Yes, so either using, so I'm going to discuss these two examples in the next two lectures, either using Hodge structures or Frobenius actions. You have methods for producing such weight decompositions. All right. Yeah, this point. Yeah, I mean, it's so general that it's, as stated, it's sort of completely useless. It's a general principle that we'll see in applied concretely in some examples. Yeah, C could be anything. Yeah, and so yeah, maybe let me rephrase this proposition, or maybe let me give a piece of data that provides such factorization.
We have a question by Frédéric. He said, he asked, can the cohomological grading serve as a weight grading?
I think not. In fact, yeah, I should have said it maybe. So it's a bit like in Damien's lecture. This weight grading, the tensor product is really, there is no causal sign rule for this weight grading. So when you tensor two things, the weight there is, when you commute two things, there is no sign involving the weights appearing. So I think the homological grading, maybe if your thing is in even homological degree, that could work. Yeah, of course. Yeah, the differential is required to have weight 0. So if you take the homological grading, that would be a problem. Okay. Right. So okay. So let me. Yes. Weights. Yeah. Let me give another proposition. So I'm going to give you a method for producing such factorization, which we'll see in action in the last lecture. So a lax monoidal functor from my symmetric monoidal category C to chain complexes. Is formal. I want to call it F. It's formal if, so as before, if it is, so here it's not quite going to be an if and only if. If it is weakly equivalent to F tilde, which is such that, well, so the first condition for this to work, we're going to require that F tilde is object-wise and degree-wise finite dimensional. So really, as a chain complex one, so not just its homology, but really want the actual chain complex to be finite dimensional. And 2 is F tilde has an endomorphism sigma which acts as multiplication by alpha to the n on Hn. Maybe it's not going to be very visible. Yeah, sorry, the definition will be split over 2 blackboards, so it's probably going to be hard for people who are online. So we check by multiplication by alpha to the n on Hn of F tilde C for all n and C. So C is an object of capital C, and alpha is a fixed element of the units of K, which is not a root of unity. So yeah, you fix once and for all an alpha, which is not a root of unity. And if you can find a model for your functors, something which is weakly equivalent to it, that is object-wise and degree-wise finite dimensional, and that possess an endomorphism with this property, then your functor. Oh, I didn't write the conclusion, right? Oh no, it's here. Yeah. Then the functor is formal. And the proof is very easy. So yeah, since being formal for a functor is stable under weak equivalences, you just have to check that f tilde is formal. And in fact, f tilde, well, maybe you consider a subcomplex in f tilde. You take the direct sum over all integers of the generalized eigenspace, for the eigenvalue alpha to the n. So for each object and in each degree, you take the generalized eigenspace with respect to this eigenvalue. So this will be a subcomplex because the differential has to preserve a generalized, the differential has to preserve generalized eigenspaces. And of course, well, this will be a quasi-isomorphism because the other eigenspaces will not contribute to homology because of this property. So this will be a subcomplex, and in fact, this will be this inclusion will be a lax symmetric monoidal functor. And of course, what you see on this description here that that object is canonically has a weight grading given by the n here. So this gives you a weight grading. This sub functor has a weight grading. And we're going to see in the third lecture that there are methods coming from algebraic geometry that lets us produce such actions on some functors. And maybe let me now state an example of applications of this method that is there's going to be a bit different from the world of compact Kähler manifolds, and I think that is going to address one of the questions I had. Namely, I'm going to discuss the case of the little disk soprod. So using this idea, you can give a nice proof of the formality of the little disk soprod. And this is actually a proof that is due to Dan Pedersen. And it's going to use the technology we've seen in Damien's talk, actually. Yeah, so yeah, the claim is chains on the little disk soprod. And it's going to be true even with Q coefficients, has a model that satisfies this the previous proposition. And the way it works, so we know from Damien's talk, we know that, well, he introduces this operating groupoid, PAB, which was a model. It was, say, if you apply the nerve construction to it, you get a model for the little disk soprod. And then well, this operad PAB doesn't have many automorphisms. He told us there is only Z mod 2 that acts on it. But then he introduced the pro-unipotent completion of that operad. And when you do this pro-unipotent completion construction, you get a much bigger group that acts, namely the Grothendieck-Teichmüller group. So the little two-disk operad is rationally equivalent And I'm going to put quotes here because you have to be a bit careful about what you mean here, because we're in a dangerous, non-simply connected, not even nilpotent situation. To this operator PAB. So using Damien's notation, I think it goes like this. The rational pluripotent completion of this operator PAB. And this guy has an action of the so-called Grothendieck pluripotent Grothendieck-Teichmüller group. So now our model will be, so now we can consider chains over the nerve of PAB Q with Q coefficients. And by functoriality, this will get an action of GT hat Q. And again, well, there are some subtleties hidden here because so we're inside of this situation that Alex explained in his lecture yesterday, where yeah, essentially this will be some kind of the Boswell-Kahn completion as a rule to this operator. And Alex said that in general, it's not true in general that the Boswell-Kahn completion has the same rational homology as what you started with. And in fact, I think, well, I'm not sure actually, but for it's a fails for classifying space of free groups. And classifying, well, purebred groups are very similar to free groups, so I expect it also fails in that case. So yeah, you have to be a bit careful about what you mean here. And actually, if you look at Dan Pedersen's paper, it's not, at least to me, it was not so clear when I was reading it, like how you really produce such a model. But now I understand it. I mean, yeah, it would take me a while to explain exactly how you do this, but you can do something like this. And now we're almost in a situation that we like. So we have this big group that acts on our model. The point is it's not finite dimensional. This chain complexes are not finite dimensional, but we have a theory of minimal models of operad. So we can find a minimal model. Which will be finite dimensional. And so by abstract nonsense, this Grothendieck-Teichmüller action, you will be able to lift it to this guy. And now, yeah, it turns out that it's very easy to compute the effect of the Grothendieck-Teichmüller group action on homology, because the homology of a little disk operad we know is the Gerstenhaber operad, and it's generated by operation that come from RET2. So essentially, we just have to understand the Grothendieck-Teichmüller action on the RET2 part of PAB. And using this observation, you can prove the following. So the induced action of GTQ and the homology of the little two disk operad is given by, so if you let an element sigma of GTQ acting on some class A in the nth homology group of D2 in RET, say P. Well, the formula for this action is just, it takes I don't know if Damien used the terminology subatomic character, but there is this group homomorphism from GTQ to the units of Q. You apply it to sigma, and then you multiply by A and yeah, you put this to the power n, where n is the homological degree of W cut. So chi from GTQ to the units of Q is the subatomic character. So this group GTQ is very, very hard, but you have this nice group homomorphism to a much smaller and simpler group. Actually, while using, Damien explained this group, talked a lot about this group yesterday. So elements in GTQ are pairs lambda f. And this morphism is just a projection. You forget the f part and you just remember the lambda. Right, and now there is a fact which is also highly non-trivial, and it's in some sense, I think, equivalent to the existence of an associator, that this chi morphism is surjective. So it follows from this that you can find, then, yeah, you pick an element of Q cross, which is not a root of unity. You lift it to GT, and that gives you an endomorphism of your minimal model that will have this property here. So pick alpha in Q cross, not a root of unity. Alpha tilde in GT, the lift. Then alpha tilde satisfies the condition of the proposition. Sorry, what? J'entends pas de. Still not hearing, sorry. Yes. Yeah, the endomorphism alpha tilde of this minimal model satisfies the conditions that I had here. So our minimal model will be finite dimensional, and this alpha tilde will act like this. Maybe I should stop soon. Yeah, maybe I'll just stop here. Okay.
Is there any question? I have one, if I may.
Okay.
You addressed several formality issues within Flashback, Opera, to connect with Marcy's previous talk. Since you began with Glenn the main point of formality of the modular opera.
Yeah.
You can say one word in this direction?
Yeah, definitely. Yeah. Actually, so the technology gets a little bit more complicated because, yeah, so these modular species of J0 curves with marked points, they have higher genus analogs where you take higher genus curves with marked points. And you still have similar compactifications that they actually form a modular operad. The issue is not going to quite be modular operad in the category of compact Kähler manifolds. Because yeah, when you go to higher genus, these objects they become actually Deligne manifold stacks. They're not algebraic varieties. So you have to sort of extend the machinery a little bit to be able to attach differential forms to the Lindemann-Force stacks and have Hodge theory in those situations. But this can be done, and they do it in the paper. And then sort of exactly for the same reason, because they know that their functor, this extended functor from the Lindemann-Force stacks to chain complexes is also formal. So then you can just feed it the modular operad of modular species of curves, and you get that this operad is formal as a modular operad. And in fact, it's quite impressive because it's not even known what the homology is. So we have a formality result where we actually don't know either side, but we can know that they're quasi-isomorphic. So yeah, the machine is extremely general. So you just you can just feed it any algebraic data that you have in compact Kähler manifolds, or maybe the Lindemann-Force stacks. You just put it inside, and it spits out a formality result.
You have a question on the chat. The answer is there's no connection. For someone who's hearing for the first time, minimal model from rational model. There is also minimal model program by rational model.
As far as I know, there is no relation.
There's unfortunately the same name.
Yeah.
Will you address in precise the stuff that you just met? That is, any kind of algebraic data, as soon as it comes from something topologically or more respecting the algebraic structure.
Mm-hmm.
Will you address this?
I'm not sure I understand your question.
You did put the journal, as far as I remember, you say, for any type of algebraic structure I have, if I start from something that has this pressure on the compact element or whatever, then when you look at the image this type of algebraic structure is formal.
Yeah, so I mean the statement was quite general. I think you can. I said at the beginning you can take any structure that is encoded by an operad. So yeah, I said so. Since we know that the functor of singular chains is formal, then if you feed it any P algebra for any say operad in sets, whenever you have a P algebra in compact Kähler manifolds, you get that singular chains over this is formal.
You said operad in sets.
Yes. No, I think, yeah, we had this discussion before. I think symmetric operads you can encode by operads in sets. Yes. I mean, yeah, yes. Yes. That's a very good question. That's it's actually well, it's very similar to techniques I've described here. Yeah, it's interesting because actually the gravity operad it looks like it should fit in the machine I've described, but it does not quite because so it's an operad structure on the homology of the non-compactified modular species shifted by one. But in fact, you can show that this operad is obtained as follows. You start with the literal 2 disks operad, and well, this topologically this has an S1 action. And when you pass to chains, you get some operad that has an actions of chains on S1. And essentially, you take the fixed points with respect to this action, and that's what the gravity operad is. And what we do is, Clément in this paper is, yeah, we show this Grothendieck-Teichmüller action. It descends to an action on this fixed points operad, and therefore, and then you can apply the same technology to prove that this is formal.
Yeah, go ahead.
Mm-hmm. Yeah, exactly. So you'll see this. Yeah, so Andrea is asking, yeah, if of course, what's crucial here is to have a unit which is not a root of unity. And we know that in finite fields, anything is a root of unity. So we have a problem, and I'll discuss this in my third lecture. In those situations, you get partial formality results. So you'll get formality up to some degree, which is related to the fact that your root of unit, your unit is eventually going to be 1. Yeah, so I'll discuss this in my third lecture.
Those of you who are starting too much characters, low characters, please come on Friday. From here to election. Or you have time and to follow the rest. Thank you.
I don't quite see the link. You started the lecture with the spoken over R, and then it said you can have a decent result over Q. But it's not clear to me how you go from one to the other.
Yeah, so I can answer in 2 ways. So in the GNPR paper, they have a descent of formality machine. And that lets you say, in some cases, there are some hypotheses, some finite dimensional hypotheses. But in some cases, when you have a good theory of minimal models, essentially, if an operator is formal, say, over R, but it's defined over Q, then it's formal over Q. And so this applies to these moduli spaces, operator, for instance. Yeah, I was hoping that, in the process of discussing this with Ricardo, so I was hoping using the technology I developed in the paper with Daniel, Dan, Felix, you can also give an alternative proof of this descent of formality result. But also tomorrow I will explain our result with Joanna is directly over Q. So I will explain tomorrow a version of the GNPR paper, which is a bit more general, that we proved with Joanna, and a result it immediately gives formality over Q, because so you don't need all this descent of formality machine.
Any question online? Is formality tutorial?
Yes. Well, your question is a bit vague, but the formality result I've stated, either formality results actually, I'm actually stating that a certain functor is formal. So so in that sense, yeah, it's functorial. But yeah, I don't know if that answers your question.